I welcome you all to the Spark Research YouTube channel. This is Dr. Virchandra, Assistant Professor in the Department of ECE. Right now, we are running in this COMSOL Research Application series, and in this session, we are actually going to, find out how to generate the different maze, how to use the parameter sweep in the COMSOL multiphysics for our photonic waveguide design applications. Before going ahead, here is the detail about the SRMIST, which is ranked on 14th as per NIR of 2025, just about to the IIT ISM Dhanbad. Okay, so we are running in this COMSOL research series, and here is the introduction about the silicon photonics. We have already discussed about the basic idea about the silicon photonics, and we are actually going to design the photonic waveguide based structure, and how to create the structure and how to estimate the different parameters, right? So here is the articles that we are going to re-implement. Actually, you can find any articles using the Google Scholar link, and if you wanted to find this particular article, you can the text these reanalysis of single mode condition for silicon waveguide at 1550 nanometer wavelengths on your Google Scholar or IEEE Explorer, and you will get the article. It has been written by the Huang. Okay, and so let's talk about. All right, in this session we are going to talk how can we modify the maze, how can we use the study, and how to find out the parameters, right? The output parameters. So before going to discuss it, let me give the glimpse about the previous session. So step one, we have to define the input parameters. Like here, I have defined H1, W1, so H2 and W2. Like that, you can define the any parameters that you wanted to define. So you can define it. In the previous session, I have already defined everything and already done all these things. So you may go through that. After that, you can go and design your geometry. Like here, first design your rectangle 1, then followed by the rectangle 2, and the number of requirements the rectangle exactly you need to design for your structure, right? After that, you can go for the material. So which domain? So this is your domain 2, which has been assigned by material air. Then this is your domain 1, which has been assigned by the silica glass, and this is the domain 3rd, which has been assigned as a silicon, right? Similarly, you can assign any materials to particular domain as per your requirement, as per your design. Then input wave, you can choose these input wave, and then finally the maze. Okay, so and then a study, and then you can simulate the structure. So in your study, you can use the lambda since I have already defined. Okay, now so let's talk about how to design the maze, right? Okay, so first this is the physics controlled maze. Now we are going to talk how to define your maze for your design structure, right? So thing is that how to design it. So user control and physics control, there are two types of the maze. First, so physics control is they will generate the maze as per the normal physics principle. User control means you can decide your maze by yourself, right? So actually in this maze, in this structure, you can see there are three different domains. What are that? So based on the domain, actually you can choose the different the types of the maze. In this example, you can see this is your silicon region, so which is the the smaller part, and this is air region and silica glass. So particularly light will confine in the silicon region. So since mode will propagate in the silicon region, so we want to study the modal analysis in this particular region. Why? Because light will mostly confine in this region. So what exactly maze is doing? So if maze is denser in the particular region means your results will be more accurate, right? So in order to do so, let's choose our maze, right? So let me remove all these and then we are going to design the maze. So free triangular we can choose, then maze size 1, size 2 and size 3. Since there are three different domain, so we'll choose the different domain. For the time being, let's suppose this is your domain 1 for geometry, your size 2, let's take this is your domain 3. Okay, then let's take the domain 2 and the size 3. So we are going to select the domain third, right? Now what is our objective? This is domain 1. So since domain 1 like is of silica glass, so we need not require to have the much more number of maze, right? So let's, this is normal, you can custom by yourself. So let it put the maximum element size, minimum element size, growth rate, curvature factor, resolution. So in this session, since it is normal and so we can leave it, no problem, normally. Then physics 2, the maze 2, this is also not our the analysis of points, so we can leave it. Actually these things will give you the idea that how can we generate the maze. Now here, now let's take the custom one. In this region actually mostly light is going to confine in this region, so we want to have the more denser maze in this particular region. So now what will we do? So you can think that what is the maximum element size? So let's reduce by 10 times, right? So now what will happen? The element size will be a smaller. So if a element size is a smaller, what will happen? Automatically your number of maze will increase and the precision in your model analysis results will also increase. Then the minimum element size, this is your maximum element size. Minimum element size, let's put it 0.2. Growth rate, okay, you can put 1.3 or 1.2, it's up to you, not a problem. And then you can build your maze. So now you can check it here. Now we have the more number of the mazes near to the silicon region. So in this way, you can increase the precision of your result. So this is a way to design your maze. Similarly, you can design your maze for your particular structure. Clear? Now let's go ahead. So after designing the maze, study. Here the model analysis we are going to perform. So number of modes you can vary to for how many number of modes you wanted to analyze. So if you are keeping one first two modes, definitely your transverse electric, transverse magnetic, T0, TM00 mode will come. Similarly, you can also analyze the higher order mode like TE01, TE20, TE30 or TM higher order modes, right? So you can choose the higher number of modes. Since this particular configuration has been designed in such a way that only fundamental mode will propagate. So I'm just keeping only two number of modes, right? So you can increase if you have the, if you are thinking that higher order mode will also propagate, right? Then search mode around, always the it will be the values mode around will be near to the high refractive index. Why? Because number the mode will be found, the having the highest refractive index near to that. Definitely it will be less but near to that. Okay, so here now I am going to add the parameter sweep. Now why I am adding this parameter sweep? Suppose I want to study the W is equal to 400 nanometer, then I want to study a W is equal to 450 nanometer, 500 nanometer, 600 nanometer. For different width if I wanted to study, then what to do? I have to, the trial method is that we will go to this W2 values and will keep on varying 400, 500, 600, 700. But it will take lots time, right? So in order to avoid it, we are directly choosing here, right? Parameter sweep. So here we are going to consider W2 and then parameter values. So what are the values? So let's suppose we are going to vary it from 400 and a step size, how much you want to vary. So let's suppose I wanted to vary by 10 and then let's vary it till 500. So what it will do? It will start from W is equal to 400 nanometer. Next value of W will be 410. Another one 420, 430, 450, 460, 470, 80, 90 and 500. So it will stop to 500. Here the parameter unit is nano scale, right? So now we can compute either from here or either from here, right? So it will give the solution. Since the number of maze is now little bit more, so it will take some more time to simulate. Once it will simulate, then automatically you will get the values, right? So it is taking some time. Apart from that, now we are going to evaluate the confinement factor and then even a scan field in this session itself. So let me see. It So it's taking some little bit more time. So probably since your session may not get longer, so I may will put the second video to upload how to find the different parameters like confinement factor, even scan field, both. Okay. So here now after simulating, you can check it. Now you have the values here. You correspondingly, if you wanted to find out the parameters, you can find the EWFD dot NEFF, right? So here you can find the mode, right? And since we have studied the simulation parameter sweep, so if you wanted to get the values, all the values for different width, then directly you can get, right? So here we have the effective index values at different W, right? So W is equal to 100, 400, 410, 420, 490 to 500, right? So how to get? Go to the derived value section, right click global evaluation and put the formula here, and then you can get the values of the all the parameters, right? Similarly, if you wanted to get the values of some more, like suppose a real part of EWFD dot NEFF, real part, then you can also get the values, right? Here is the values, real path values for different width of your rectangular waveguide. Similarly, if you wanted to find out some more values like propagation loss, then formula you should know. Formula is what? Formula is the 10 log log E and then 4 pi imaginary of your imaginary part of your vector index and divided by your lambda. Using that you can find out. So now, since I have already copied, so let me use this formula. This is your propagation. You can find this formula in your article, and you can similarly use any formula to find out your value. So this is in your centimeter. I am just putting, otherwise it will give in meter, right? So formula is your 10 log E and then 4 pi imaginary part of your n effective and then divided by the lambda, right? Now simply we'll evaluate. Now you can check, we got the values of the propagation loss as well. These are the values of the propagation loss, right? So this is the way to get the values of the refractive index, real part, imaginary part, the propagation loss. Similarly, you can also get the values of imaginary part, also E, M, A, G, and then EWFD dot NEFF. This will give you the value of imaginary part, right? And now after getting the values, Now if you wanted to plot the graph, you can plot the graph, right? So here we got the imaginary part. So this is very easy to get all these values. Okay, now since session is going longer, so I am avoiding to calculate the confinement and even scan fit. So we'll talk about it in the next session. Thank you. Thank you to join the session.